So if you recall, we've covered the idea of stress, and we covered that there are 3 equilibrium equations and 6 stresses. And so we don't have enough equations to solve for stresses. And so we have to continue our hunt to understand how to better predict and how to predict the failure of structural systems that are subjected to external loads. And one concept that is of critical importance in our hunt in trying to understand structural systems is the idea of strain and deformation. So let's dive into that topic. It's a very important topic. So it turns out that a structure deforms, and you guys all agree that a structure will deform when you apply a load to a system. And that load will produce a deformation in such a way that will change the dimensions of the body of material, like a wing or something else, and it will also change its shape. Deformations also induce strains throughout the whole structure. So they will, and I'll explain what strains is a little bit later. Strains is defined as a measure of relative deformation of the material and is such that they're directionally dependent. So the strain can also be different in each direction. But strain is a good measure because it's a relative deformation. It's a measure of relative deformation. I'll give an example coming up. Now, strains are really good quantities to look for because you can actually measure the strain using strain gauges, which is an instrumentation technique to measure the strain on the surface of a structure. More modern techniques include digital image correlation, where you put a speckle pattern, and the speckle pattern with a spatial video system allows you to record the strains across a structural system. And that technique is used with quite a bit of high confidence to be able to take 3D measurements of deformations, displacements, and can be used in combination with strain gauges, and is able to measure complexities that are not possible with strain gauges, because strain gauges can be applied locally in various areas, while digital image correlation can provide a continuous field of view across a system. And that particular technique is a non-contact optical technique that can tell you quite a bit about the structure. And so that's why that technique has become modern and has been part of some of the, I have been able to use it in a lot of my work in aerospace design. Deformations and patterns can be visualized with DIC. And so that is a good way. Now, in contrast, when you look at stress can also be measured, but usually can only be determined indirectly by measuring some force or trying to do a numerical simulation. So an advantage is strain can be measured, and it can be measured directly with high confidence. That's why we would like to look at strain. Let me show you this picture here. In this picture, this is a test of a Boeing aircraft, which has attachments that try to simulate the loading environments that this wing is going to see in service. Each of these straps that applies loads in a non-uniform way, such that the loads are non-uniform across the wing and try to best replicate the environments it's going to see in service. As you can see, this particular tip is moving quite a bit. It can move upwards of 30 feet. And this tip that's moving upwards of 30 feet, just because this tip is moving a lot, it doesn't mean that that is the location where the highest strain occurs. In fact, most likely at the tip of this aircraft, you probably have the lowest possible strain at that location. or maybe it's high, but we don't know that. The strain can be higher somewhere along the wing. So just because the deformation is large, it doesn't mean that the strain is the largest there. The strain is going to be large at a location that may not be the one that deforms the most. So, but are the strains large enough to break the structure? And how do you know where these strains occur? That's why we use the concept of strain, because if I went by deformation, you may say, well, it's deforming a lot here, so it's going to break here, but not really. It's probably going to break more where the strain is largest. And so that's why strain is a better measurement for determining whether structure fails.
I don't think you pressed record again. You just started recording.
So the deformation can be broken up into three: rigid body rotation, so you can rotate the body with no stress applied; rigid body translation, you can translate the body without applying any loads, so no strains form; or you can stretch and distort the material. Here in the next slide, I show you the different things that could occur. So I have an undeformed element here. If I rotate a rigid body, this will have no strain. If I now stretch it horizontally, it's going to have strain, probably more in the horizontal direction. If I strain it in the vertical direction or apply load in the vertical direction, it's going to stretch in the vertical direction. So it will develop strain in that direction. If I distort the body of material, it will shear, as you can see in the bottom right. So this will have straining as well. So the bottom three are the three modes of deformation that when you superimpose these three modes of deformation, then is the kinds of strain states you will see in a real application, typically. Here you can see on the deformed material on the left, when I apply a load on the top, the material deforms as you see here on the right, as an example. So this body will stretch, and then it's also going to have shear or distortion. Okay, so let's study now one mode of deformation. So say I have this bar, and I know this is very busy. I'll go to the next slide and do go a little bit slower there and a different method of doing. But say I have this bar and I draw a line. I will draw a line, and that line that I have inscribed with a marker, like a Sharpie, has points A and B also. I'm naming the ends of that line, basically. So say the location of that point A is X apart, and I consider a small differential element, AB, that has a measurement of delta X. What I'll do, this body of material, which is a bar, has length L sub 0. I'll stretch that a little bit, an amount of delta. Delta divided by L sub 0 is a good way of measuring deformation because it's normalized against the original length of the material. So if del is 0, then you know that there's no strain. But if del is L sub 0, you know that it's stretched an amount of 1. You can see it's a non-dimensional quantity. There are many different ways there's many different ways of defining strain. This is one of them. Here in the bottom right, what I've done, I've taken this bar and stretched it by applying a load P. So what happens? That point A obviously is going to move downwards. So that point A moved displacement U downwards to point A prime. That point B also moved downwards to B prime, and that's going to be an amount U plus some delta U, some extra, because A prime moved an amount U, point B is also going to have to move an amount U, except that it's going to have an extra deflection because this line could have stretched beyond of what A prime moved. And that's the amount that delta U is. So what is the strain at A? The strain at point A is basically the relative deflection of UB and UA. So UB, the relative the movement of UB and the relative movement of UA. UB minus UA tells me the change in length of that line segment AB divided by the original length delta X, which is the distance between A and B in the original configuration. So that's the original length, delta X, while UB minus UA is the relative deflection between A and B. When you do the calculation, you find that you get delta U divided by delta X. Because U and U cancel, when I substitute it here, U and U cancel, so I get delta U divided by delta X. And if I take the limit as delta X goes to 0, I get du dx, the derivative of the deflection U respect to the derivative with respect to X. So that's what you get here using this method. Let's use a slightly different method that uses coordinates to better understand what is going on. So let's try to understand how the strain in the X direction can be calculated. So say I have a square and I will call this point Q, and this point I'll call it D. Point Q is going to move to where Q prime is. So this is your new location. And then D is going to move all the way where D prime is. That's your new location now. So I applied loading to that square in such a way that that square deforms such that it looks like the one here. Like the one here, the rectangle on the right. You can see that it's stretched a little bit. Okay. So how do I calculate strain? We discussed it. So one approach, there's many others, is to take this final length, Q prime D prime, you can see here. I'll subtract the original length, QD, and I'll divide that by the original length. So in essence, I'm normalizing to the original length to understand how much more stretch compared to the original length. That's the idea here. Did it stretch a fraction of it? Did it stretch almost equal to that initial length? How did it stretch relative to QD? And that's a very useful measure of deformation, because you know the deformations of the system physically. So if I can tell you what the deformations are at the end, that is very useful. So let's see. We can try to calculate these things, and we'll do that. But it's easy to see that QD here, I'm using a differential delta X, element delta X, which makes it easy now because I can plug in delta X and delta X here. So what is left now is really to calculate Q prime and D prime. And that looks like a lot of work and sounds difficult to calculate this distance. But we can do it together. For example, Q, that coordinate Q that you see there, the coordinate for point Q, can be calculated. The coordinate for Q, let's say arbitrarily, is XY. So I'll call this coordinate here Q, XY. So then therefore D has to be X plus delta X in the X coordinate. So X plus delta X, because if this is X from here to here, then D, the location D has to be X plus delta X. There's no choice, right? The height in the Y direction did not change. So D is in the same height as Q. So since the height for Q is Y, then the height at D is also Y. Okay, excellent. We're getting there, right? We're getting there. You can see there that we can now do Q prime, for example. So for Q prime, I want to call U the deflection in the X direction. So let's call U the deflection, how much it displaces. That point displaces in the right direction, in the X direction, I meant. So what we're saying here is I have the deflection, the coordinates of Q prime are going to be U plus X. So if this was X, this distance here is X. How much this displays all the way from Q to Q prime? I'm going to call the distance between Q and Q prime the new deflection UXY. So if it deflected from Q to Q prime, and that's the deflection UXY, then the coordinates of Q prime has to be X, where Q is, plus that extra amount that deflected from Q to Q prime. So that's why it's U, X, comma, Y plus X. And the height of Q prime has not changed. It's still Y. Just like D and Q. They both have the height Y. I can then calculate the point D prime. For D prime, what you notice is, I look at where D is. D is at a location that's X plus delta X. So X plus delta X, but that D moved from that point all the way to D prime. And that deflection is U, but that's evaluated at this point because that's where I'm measuring the deflection. And that point is measured at X plus delta X. And that's why you see in this parenthesis, I have X plus delta X. But the height is also Y because it hasn't changed in height. You can see that there. So just to make sure the concepts are clear, if I were to translate the square to the right and it didn't stretch at all, it was just pure translation, no strains will be forming within the square. But in this case, this square translated and also stretched a little bit. So you expect some strain to form. That's the first question that could come up. The second question is, what does this Q prime really represent? Let's think about it. What I was trying to point out is that this corner Q is moving to a new location Q prime. This corner D is moving to a new location D prime. Every corner is moving to a new location. Every point within the system is moving to a new location. How much you moved is the displacement U, or the deflection U, which varies across the square. So this point moves an amount here, this moves a different amount, this moves a different amount, but in aggregate, the movement causes the structure to look different in a new configuration. As a consequence, if I look at Q prime, you can see that Q prime will be then the distance between the origin to Q, which is X, plus whatever amount it moved. And that amount, as I stated, is reflected by the variable U. U, which is evaluated at the point where I'm going to be doing the calculation, which is here. So it deflected an amount from here to here, but it's evaluated XY because that's where I'm looking at. That's the location where it's going to move from. So if I look at D prime, same thing. So D is here, and that location is X plus delta X. That's that location right there. And then that point moves all the way to D prime. And so that makes sense that I have an X plus delta X to represent that distance there. And then that new coordinate has to be plus that deflection from this point all the way to this point. And that deflection is evaluated at this coordinate D because that's the location I'm evaluating that deflection. So X plus delta X, because that's the coordinate of that point, comma Y. So that's where we are right now. And now it's very easy to calculate that distance, Q prime, D prime. All I have to do is to subtract this coordinate minus that coordinate. And I've done that here. Look at this. Q prime, D prime is going to be this distance, D prime minus Q prime, the location of X here and the location of X here. So if I look at it, what I've done, I dropped the Y because Y is useless here. Y is the same for every single one of this. So it's not worth keeping that around. So I removed it. So let's look at this. So I took this component of X, which is D for D prime, this one right here, subtracted the component for the X coordinate for Q prime, which is right here. I just translated that, I just copied that over. and I copied this over, the x component of that coordinate. When I do that subtraction, you notice here that x cancels out. And so I get this minus ux plus delta x. Perfect. We also stated that QD was delta x. That was earlier when I talked about I made this delta x. So now if I plug in what Q prime D prime is, which is this expression here, which is here at the top, I put it here, minus QD, which is delta x, divided by delta x cancels out. And you get the epsilon xx, which is the strain. That's how I define strain. I define strain, the final length, minus the original length, divided by original length. And that's one way of measuring strain. I get this expression. But this expression is really partial u respect to x. If you remember back in school, as the limit of delta x goes to 0, this expression turns out to be the partial u respect to x. You also know that from Taylor series expansion. You may remember from Taylor series expansion that u x plus delta x equals u of x plus delta x partial u respect to x. You can see that this expression at the bottom is true because you can see that that's equivalent to what's above. So in other words, I derived the expression for strain differently from the way I did it here in this slide. This to me is more formal and a lot more clear than the previous method. I can then repeat the same process for the other strains, the other directions. I can do the same process in the y and the z direction. So if I call v the deflection in the y direction, then epsilon the strain in the y direction, which is the strain this way, that strain is partial v respect to y. And finally, out of the plane of this page, w is the deflection out of the plane of this page. Epsilon zz, which is a strain out of the direction of this page, is partial w respect to z. So you have three strains here related to three deflections. Now let's look at something a little bit more complicated that's going to take a little while to explain. But here, what you see is the shear strains that we're going to talk about now. Because we talked about the ones here cause the body to stretch, such as this one here. So that causes either this or that. So these strains epsilon xx, epsilon yy, and epsilon zz cause the body to stretch or compress. But the ones I'm going to talk about now is going to cause the body to distort. And that only happens when you apply shear loads. So let's look at that now, but you need to be patient with me because it does take a while to really get a hang of it. So let's start with this point Q. I'm going to track this point here first. It's going to move to this point right now. So let's look at Q. So Q is at X and Y. The coordinates, you can see that there. The coordinates here are X, comma, Y. And you can see that makes sense. That's the location of that point. Point D is the same height, Y. So that makes sense. You can see that there. It's the same height, Y. But the X coordinate is X plus delta X, which makes sense because this location, this right here, is delta X. So X plus delta X gives you a new coordinate for D. So I think that should make sense. Fairly straightforward, nothing fancy there going on. So we covered this point. But now let's track Q prime, which is this point here. So Q, this point here moved all the way where Q prime is. And what you see here very quickly is that that coordinate is easy to calculate because it's basically it moved a value of x to the right, but it deflected a deflection u all the way to the right. So that deflection u is this one here, u plus x. And then that point D, sorry, Q, I'm still on Q. Q also moved up. It moved up. So the deflection, and remember, anything that deflects in the x direction is U, in the y direction is V. So it moves to the right U, it moves up is V. And you can see that point Q moved up also. So what is it? So is a height Y plus a deflection V. And that's what you see there. V plus Y. Okay. So far, I hope you're following. Okay, so one question I want to clarify is that U and V, the deflections, U, V, and W can vary across the whole system. You know that because let's look at this wing. That wing, you can see it deflects a lot more here than it deflects here at the root of the wing. So clearly U, V, and W are going to vary as a function of location quite a bit. So that's something to keep in mind as we go through this. So we tackled Q prime. We know how Q moved to Q prime. But now we have to tackle how D got to D prime. So that's not that hard either, because what is it? So let's look at it carefully. D, the point D, moved all the way to this point here, D prime. But on the right, you can see move from here to this point here. Okay, well, that is not hard to figure out because that coordinate is x, this x here, plus delta x, plus the deflection from there all the way to here. But the deflection, isn't that just the deflection of this point U evaluated at x plus delta x, comma y, which is exactly what the coordinates of D are? That makes sense. That's what the x coordinate should be. It should be x plus delta x because it moved at an amount x. Sorry, it didn't move an amount x. Let me repeat that because that may have not been clear the way I said it. Let's say it again. So I'm trying to evaluate how this point D got all the way to D prime, but only in the x direction, which is deflection U. So I'm looking at the x coordinate. I'm trying to figure what the coordinates are. So this point D is located at an amount x plus delta x, which is what you see here. And then it moved, then that point moved all the way to the right here. And that deflection is U. But that U is evaluated at the coordinate here where D is, which is x plus delta x, comma y. And that's what you see there for D prime. So hopefully that is clear because it's not easy. Again, even for me today, it took a while to figure out. And then I have to figure out the y coordinate. The y coordinate is not that hard. We know that this point y moved up. So it moved how much? It moved this y amount, which is what you see here. And then it moved an additional amount. It didn't move. I'm sorry, it didn't move. D was already there. So that amount is y, as stated here. And then that point moved. Exactly. Now it moved. It moved all the way, deflected all the way there, which is U, V, a deflection V because it moved up. And is evaluated at the location where D is, which is x plus delta x, comma y. So that's what we got there for D prime. And we have to do one more, which is B prime. So B moved all the way to B prime. So let's look at Let's look at B prime now. So B moved all the way to B prime. Now, let's look at the X coordinate. The X coordinate is going to be, it moved, it didn't move, but that location B is how much is X? And then that did move all the way to this point B prime. So that's where you see an X there. And it moved an amount U, deflection in the X direction, but is evaluated at the location where this coordinate is. And that coordinate is obviously X, because that's X. And it's Y plus delta Y, because that's Y and that's delta Y. So that's the coordinate for that point, which is X, comma, Y plus delta Y. So that's why B prime has an X coordinate or coordinate that looks like that. Okay, and I'll erase all this stuff so it's not too messy and we don't get confused. So now let's look at the B prime, the coordinates of the Y coordinate. And so what I'm looking at how much this point moved up and what is the new coordinate for that point? Sorry, not all the way up there. Somewhere here to this point. I don't know how much it went all the way up there. So it's what is Y plus delta Y plus this deflection V. So it's what? V plus U plus delta Y, which is exactly what you see here. Y plus delta Y plus V, but evaluated at the coordinates of B. Because that's the one I'm looking at. That's the one I'm trying to track, right? I'm kind of tracking these points to figure stuff out. Okay. So that concludes how you find these coordinates. When a body of material distorts, what is actually useful to figure out is what are these angles, because that's what's telling me how much things are distorting. So what I'll do then, I'll calculate what the tangent of alpha is. So tangent of alpha is this height divided by this length. And the way you calculate that, you subtract the y coordinates. So you subtract this point to this point, and that's going to be subtracting the y coordinate for D prime and the y coordinate for Q prime, subtracting those two. You can see there that y cancels out when I subtract it, and I get exactly what you see here in the denominator. Because the tangent of alpha is the opposite divided by the this right here, the adjacent, right? So that height here is this minus that, which is what you see in the numerator. In the denominator, I have to subtract. I have to figure out this distance, and that I find by subtracting the x coordinate from here and that one. So the x coordinate of that is this, and the x coordinate of this is this. So I'll subtract both of them. You can see here that x cancels out, and that's what I get here in the denominator. So that's how I find the tangent of alpha. What you notice here is that this is actually equal to the partial v respect to x delta x, which is what you learned back in Taylor series expansion. And I actually just applied it here earlier with this formula here. And then the bottom one, you can see here that this simplifies to this also by using Taylor series expansion. And then delta x cancels out. But what happens here is that actually what I'm going to do, I'm going to remove this from here, factor delta x out, delta x cancels out, so you get a 1 here. And because du dx is so small, like here, I'm exaggerating the deformation so you can kind of see. I'm exaggerating a lot so you can see how things deform. But in real life, these are very small deformations because the strains, even in this aircraft, this wing that's deforming quite significantly, at ultimate loads, which they apply a factor of safety of 1.5 for airplanes when they apply a load of here, for example, the strains shouldn't exceed more than 2%. So they're quite small strains. And so most likely for large, even for large deformations, but most likely this is going to be small compared to 1. And so therefore, what you get is delta x canceling out. This is close to 0 compared to this one, which is 1. And so you basically get dv dx divided by 1. So tangent of alpha is approximately alpha. You can check that with your calculators. Put a value of alpha that's small, like this alpha here small. And then you get that's similar to alpha. And then these approximations here give you dv dx. So that's how I found the angle based on the deformation I showed you now. Okay, so now I'm going to repeat the process, but now for beta. So this beta right here. So now what I have to do is figure out this distance here and also this distance, because now I have to calculate tangent beta, which is this distance here, which is the x coordinate difference between b prime and q prime. So I'm looking at subtracting this coordinate from this coordinate, which goes up to there. Nope, that's not the right one. B prime is this one, and then Q prime is this one. I have to subtract that. And you can see here that X cancels out, and you can see that in the numerator. Tangent beta has in the denominator, I have to get this height here, which is a Y height between the B and Q prime coordinates. And so I have to subtract this minus this. That cancels Y for me. You can see that there, Y cancels. So once I have that, you realize quickly that this and this combine to give you this derivative. This at the top gives you this right here. And again, same thing, delta Y cancels out. You get a 1 here, but this derivative is very small compared to 1. So you end up getting du dy. So that small angle approximation again, tangent beta is approximately equal to beta. So I get the beta equals the partial u respect to y. So what is the angle change then, physically? Because that explains the distortion, right? The angle change. So it started at 90, but it deformed to this shape and this shape. That's how much it deformed in terms of angle. So alpha plus beta then is what I care about. So the shear strain is defined as alpha plus beta. So I took the alpha, added the beta to it, and that's really the total change in angle starting at 90 degrees. It started at 90, but it changed this amount. So the shear strain is a measure of distortion. You can see that happening there with my calculations. And I can repeat the process now in the other two directions, and what you get is these formulas. The way to memorize it, the way I memorize it is the following. Partial of xy is the angle change or angle change. And is equal to, the way I memorize it is, I put partials like that. I know it's x and y, so I'll put x and y. And then on this one, I will put v, because that's the deflection in the y direction. And here I'll put the deflection u, because that's the deflection in the x direction. So that's the way I memorize it. You can do it other ways. But that explains physically what that shear strain is. It tells you exactly what it is in terms of the physics of the problem. So at the end of the day, there are 6 components of strain. 3 of them cause the body to stretch or compress. 3 of them explain distortion or angle change. So, and not only that, we did something cool. We related that to actual deflections of the body of the material. Beautiful thing is I can measure these strains. You can actually measure strains, and it's very doable. Now, when I look at the strain tensor, which is in the right-hand side, you'll notice that I don't see a gamma. That's because these ones are going to be twice epsilon yz, yx. They're symmetric too, by the way. So they're equal. This is equal to that. Twice epsilon zy, and this twice epsilon xz. And so what goes in here then, for example, that one is 1/2 gamma xy. That'll be 1/2 gamma xz, and so forth. The strain tensor is symmetric. The strain tensor is symmetric. So with that, I want to ask if strain tensor is symmetric. You can see there's 6 of them. There's 6 equations here. 6 strains and 3 deflections. They're all unknown. So therefore, we need something called the compatibility equations, which I'm not going to go into details because I explained the derivations in my book. But it turns out that these 6 components of strains here, or this 6 strain deflection relationship, satisfy something called the compatibility equations. And they do satisfy them to ensure single value solutions exist. Because if I have 6 equations and I have 3 deflections, I have more equations than unknowns. And so as a consequence, I need something that ensures compatibility. And so these equations do that, and they do that, and it can be shown automatically that they're satisfied. And they're in my book. You can check it out there, the derivations for that. But I won't spend too much time on this particular topic here. This is more for your information at this point in time. Similar to stress transformation, one can derive the strain transformation, and you get the same equations that we got before, pretty much. They look very similar in nature if you compare them to the stress transformation. And finding the principal strain orientation is given by this formula, and the principal strains are given by this formula. Pretty much the same formulas we had before, but now instead of stresses, there are strains. Maximum shear stresses also are used with can be found with the same formulas, the orientation of it, and also you can find the maximum shear strains using this formula. You can also take the maximum principal strain and the minimum principal strain, subtract that, plus minus, and that gives you the max shear stress. So same formulas we have for stress, they also apply for strain. You can do the same thing where you actually calculate the principal strains and directions using the eigenvalue problem. So you take this strain relationship, you subtract lambda from the diagonals, and you find the determinant, and you set that equal to 0, and that'll give you a cubic equation that can be solved for the 3 principal strains. Something very cool happens if you add the diagonal terms. It doesn't matter in what orientation system, if you coordinate system, if you add these 3 terms, that tells you how much the volume of the volume element changed. So if I have a body material that has not been deformed, if I take a little cube Now I apply loads everywhere, but I take the same cube. After I apply the load, it will deform, it will stretch, it will do whatever. Adding these three terms tells me how much the volume changed from here to the new configuration. So that's kind of cool to know. It tells you the change in volume divided by original volume, which is kind of cool. You can also transform strains in 3D just like I did before with the formulas I showed you, where you calculate Q, the transformation matrix Q, and you can calculate new strain using the very formulas I discussed earlier. These are matrices. So if I know the strains in one coordinate system, I can apply this transformation Q and to get the strains in the new system. Strain measurements can be actually performed using strain gauges. It works by measuring the change in electrical resistance across what we call a Wheatstone bridge. And these strain gauges are bonded to the structure you want to measure the behavior and deformation. Here I have an example. So consider that you have three strain gauges are bonded at some angle theta A, theta B, and theta C. So say I have these three strain gauges here, A, B, and C. And say I measure the strains going in this direction, this direction, this direction, and this direction. But then I want to know the strain. So I bond these strain gauges, I bond them into the wing of an airplane, say at a location where I'm worried about what's going on. One reason people use strain gauges in a system and apply them to a system, a structural system, is so you can then take that and validate your models, right? You can use that to validate finite element models, for example. Very useful quantity to have. It turns out that if I'm able to measure these three strains and I'm using instead of E1, it should be EA. So I'm using E1, E2, E3, but this is basically 1, 2, and 3. I apologize. And this will be your theta 1, theta 2, theta 3. All you have to do is plug in the location of these strain gauges, so this will be fully known. If you know these strains from the measurements from the test, you can then calculate the strains in the global orientation systems, the Cartesian X, Y, Z. So I can tell you exactly what is going to be in this system. And that's very useful in for a lot of reasons. Let's start with some examples here.